So we should be fine to start. Welcome back, everyone. I hope you had a good week. We'll continue our LAMMPS course today with the last session. Just to remind everyone once again, these are recorded. So if during the sessions you ask any questions with your audio will be recorded. If you do not wish that to be the case, just post your messages, your questions on the chat. With that in mind, if there's any questions from last session, that anything that came up during the week, if you tried any further exercises, we can start with that. If anyone has any questions, seems like there's no hanging questions. Great, we'll start today's session continuing from last week. So last week we went through the input file for LAMMPS, and we looked into what the major important commands are to run a LAMMPS simulation. Today we'll have a look at the output file from that simulation we run, and then we'll go a little bit more into depth into a few of the computes so that you can calculate properties during your simulations. We'll have a look at variables and loops inside input scripts. That's a very quick thing. And then we will have a quick look at how to use GPUs with LAMMPS on systems that support that. And then finally, if anyone is interested in either compiling or delving a little bit more into input creation, we can have a little bit of look into any of these. I'll put up a poll later into deciding whether people are interested in any of those things. Okie dokie. So we'll have a look now at the output from exercise 2 from last week. So I hope everyone can still log in into your accounts in ARCHER2. If not, Arno is around and can help you individuals. Just message in the chat, and Arno will give you a hand. Let's have a look at our output files. So we have our log file that was created when we run our simulation. This is created by LAMMPS. The default name will be log.lamps, but in our submission script for Slurm, we modify that to give us the job ID so that there's no overwriting if you run the same job twice, for example. So let's have a look at that and go to the top. So the first thing you'll see is that LAMMPS tells you which version was running and how many OpenMP threads it used per MPI task. Later on, it will tell you how many MPI threads it did. And then LAMMPS actually just writes every line of the input file to the log so that there's a history of what LAMMPS run and how and when. And in between some of these input files, you'll get new output from any sort of calculation that LAMMPS starts to do, or any setup that LAMMPS needs to do and thinks it's wise to give you some feedback. For example, if we see here, we had defined our lattice as a variable at the beginning of the file. So here, when LAMMPS encounters that variable, it prints the line twice with the variable replaced. This is very useful whenever we're trying to debug any kind of loops or variables to see why our loop is not behaving as we would expect it to. For example, LAMMPS prints us the values for us, which is very nice. Afterwards, we can see LAMMPS is creating the lattice spacing that we define based on the density, and then starts creating orthogonal boxes. And then here, perhaps useful sometimes, it tells you the composition of the three-dimensional space and how LAMMPS is going to split that. So here, LAMMPS split our simulation box into 4x4x8 grid, and LAMMPS does the composition automatically and tries to be the most efficient as it can in terms of communicating neighbors. this will continue for a while. It will even give you some stats of how some of the steps take until we get to our run command, which tells LAMMPS to actually start the simulation. And here we'll transition into just output from that simulation. The first thing, LAMMPS will go through generating any mixed pair coefficients if we have any. So for example, if you just define the Lennard-Jones terms for separate atom types, but then tell it to use geometric mixing for both, then LAMMPS can automatically generate those. At this point, then LAMMPS will generate the first for the first time the neighbor lists, just so that each CPU, each MPI thread has a neighbor list for all the atoms that it's going to have to take care of. And then once that's done, it gives you an indication of how much memory it thinks it will use per MPI rank. These tend to be fairly accurate at the start of the simulation, but depending on what kind of system you have, these might increase during the runtime. So if you're calculating things and keeping track of any kind of property, these might increase during the runtime, but it gives you, but at least it gives you a decent idea of how much you can expect to use per MPI thread. So if you can judge whether you can fit a much larger system or not in your compute resources. And then we have the output from the thermodynamic information. So from, if you remember, from the thermo and the thermostyle commands, we told LAMMPS to output information every 500 time steps. As you can see on the first column on the left, every 500 time steps we have a line. And then we told LAMMPS to output information on temperature, total potential and kinetic energies, pressure, volume, and density. Because we have fixed volume and density on our ensemble, those are always constant. The pressure varies, and even though we're trying to keep the temperature at 1, the thermostat will allow some variability across the simulation or along the simulation, but you'll see that it's always hovering above, just above or just below 1, and you can influence how much of that variability you can have by your T-damp parameter on your fix. After, so we're running this for 50,000 time steps. Once that's complete, and because we do not have any other run commands on this input or any other commands for that matter, the run command is the last one, we get some information on that, first on that run command, and then later on the entire job. First here, this line tells you that LAMMPS took 4 seconds on 128 processors, I believe, to run 50,000 time steps on a system with 1,000 atoms. So this can give you an idea, for example, if you're trying to compare your system with a different one, to have an estimation of how long it can take or not. These are not always simple calculations, but it can, for back of the envelope calculations for estimations, it can be useful. Then we had seen this line before with nanoseconds per day on the other simulation. Here, because we're using Lennard-Jones units, we're giving tau per day and time steps per second. Again, this is performance. It can be useful to see how long a simulation will take if you want, in this case, for example, if you wanted 10 to the 9 time steps, how long would that need to run? This is especially important if you're running small benchmarks to then prepare for larger runs. And then it tells you how much of the CPU time it was able to use, and then how many MPI tasks and how many OpenM3 threads LAMMPS used. You should always double check that these are correct with what you expected, so to make sure that you're launching your jobs with the correct Slurm setup, to make sure that you're not underpopulating nodes, for example, if that's not your intention. And then a very important table. So the MPI task timing breakdown table that you can see here, this tells you how the time was spent, in what parts of the LAMMPS routines time was spent most in the last run. You'll want to minimize as much as you can communication time, because those are the overheads of sending and receiving data from process to process, from node to node. This is not calculation time. So during these times, your CPUs are usually not doing any actual MD simulations. They're just sending, receiving data, or waiting to data to be sent or received. This percentage of 76% is really bad. So we are using probably many more threads than we should for such a small system. And indeed, 1,000 atoms for 128 threads is very much overkill on the number of threads per atom, or atoms per thread, I should say. This table can have up to 8 different lines. In this case, because we're not doing any kind of bonded or long-range interactions, those lines are omitted, but you could also have them. I'll go through these in order just to explain a little bit of what they do. Pair refers to any kind of non-bonded force computation. So in this case, the Lennard-Jones interactions. So we're having about 7% of the total time. You also have a breakdown of the minimum, average, and max time that is spent on non-bonded interactions. This is minimum time, average time, and maximum time for the entire run command, and depending the minimum time any thread used and the maximum time any thread used. The maximum times might be for different threads on different lines, and the variability is also calculated for you. So the variability from the average is also calculated for you, and it's a useful measure of whether your simulation is balanced, is split evenly across your available resources or not. So if you have your variabilities here quite high, like we do here, you might want to look into balancing your simulation a little bit better. I can point you to the balance and fixed balance commands. We covered that a little bit more in detail on the advanced course, but if you want to have a look at those in the LAMMPS manual, the explanations are fairly good. And the other, so here we only have non-bonded interactions. You might also see bond. So that includes all bonded interactions, including calculations of angles, dihedrals, and improper angles. And then you might also see k-space. That is for any kind of long-range interactions, like Coulombic interactions, for example, using any of the different methods, UWALT, PPPM, or MSM. And then next we have neighbors. So this is the construction of neighbor lists. The more often you do that, the more this increases. It doesn't usually take that long, even if you calculate it every time step. But if you can save a few percent here, as long as you're not running into any kind of dangerous build territory, you should. Then communication, I've touched on this. This is what we spend most of our time, 76% on the simulation. And again, this is because we have too many threads for the number of atoms we have. You should aim to have as little as this one as possible, and then for things like k-space and pair, maybe 10 to 30% is usually a good thing to aim for. Next, we have output. This is any kind of writing of files, being it log files or dump files, or any kind of property that is computed, and we'll look into how we do any of those in the next lesson. Any kind of writing to file comes into this section. Modify is the act of actually calculating the fixes in the computes. So this can be usually about 10 to 20% as well, depending on how many things you are calculating. And then lastly, other is anything that's not covered by any of the other names, labels, basically. Then we have some quite dense information about neighbor lists, neighbors, and ghost atoms. This can be a little bit confusing, but it can give you some nice information about again, the balance of the distribution of your system across your processes. First, you have how many local atoms each processor is responsible for. Here we see that they are on average 7.8, but between 5 and 12. That's very low number for each core, and thus is why we have such high communication costs. But then we have an histogram. It basically divides the values for each of the thread into 10 bins and gives you an histogram. So you can see whether your distribution is fairly homogeneous or whether you have a bimodal distribution or any kind of other distributions that you might then be able to fix using any kind of computes or balance commands or anything like that. And then you have the same, but for ghost atoms. Ghost atoms are the ones that are within the cutoff distance plus the neighbor skin, and then you have just the actual neighbors that each thread owns for all of the atoms that it's in charge of. And again, the histograms for those two things. And then finally, you have some more information on neighbors, and especially interesting is these number of neighbor list rebuilds. So in this case, we're always rebuilding every 10 time steps or so, and then the number of dangerous rebuilds. You should aim to get 0 here. Having so many means that every time the neighbor list was rebuilt, there was at least one atom that moved more than half our skin distance, and we to make sure that our simulations are physically true, that we're not missing any kind of forced interactions, we should aim to have these at 0. What would mean here is that we would have to reduce the delay on our neighbor list rebuild so that they're checked more often, and then they're rebuilt every time much more often so that they move less between each rebuild. We could also increase the skin distance, but that usually has an exponential effect on the number of neighbors. Maybe not exponential, probably cube, but a very large effect, and that can affect the amount of memory you need per thread. So if you have some memory to spare, you might want to do that instead of the more often rebuilds, but both approaches are valid. And then finally, the total time that the LAMMPS ran. This includes reading inputs, writing outputs, and running the simulation. So if you had several run commands in a row, you'd only get this this line at the end of the entire command. Does that make sense? Is there any questions about the log files? Okie dokie. We can then have a look at a few more advanced input commands then. And for this, we'll have a look at the files in exercise 3. We'll run some of the files here and then have a look at the commands there as well. So we have the Slurm file here has 3 different strun lines. For now, we want to keep the first one uncommented. Make sure that your account is TA. I have updated the files on the shared folder, but make sure that that is correct, TA181. And you should be able to run this again with sbatch sub, and then we can have a look at the outputs from that, and as well as at what generated them. So let's see if this has already finished. That is running. There we go. We have a bunch of things. I will show you. Most of this is very similar to exercise 2. The differences will be down here. We're doing a few more things. For example, these two commands here, dump and dump modify, these are used to save the positions and velocities of the atoms at every X number of time steps. In this case, we have here 100. This saves it to a .lamps trajectory file, and then you can use this with other software to either do any kind of analysis on the atom positions, or to create visualizations of your system, being them static images at a specific time step, or you can even create movies of your systems moving, your atoms bouncing into each other, or generating structure, self-assembly, any kind of that thing. That is how LAMMPS does this. For most systems, you do not want to dump every time step, because the file sizes can increase very rapidly. Even 100 for most systems is overkill. Depending on how fast your molecules move, you might want to increase that to 1,000 or even more. And also depending on how much available space you have. Be aware that dumping fairly often does increase the runtime, because while LAMMPS is dumping data to disk, it does not continue the simulation. So if you are writing to file very often, this can increase your simulation time quite significantly, like in the 10% range of performance loss. And then finally, the dump modify here just sorts the atoms by their ID when dumps is dumping, so that you then have an ordered list of the atoms that is always the same, rather than having a random order of them every time step. You might need this, you might not care. If you're just creating movies, this is not really needed. If you're doing any kind of analysis afterwards, this might be useful. Use at your own need, basically. Let's have a look at how a dump file looks and exactly what kind of information is in it. In this case, maybe should have mentioned just a few of the flags here. So similar to most of the fix and the other commands we have a dump ID. This just identifies which dump this is, and then the modify one is modifying this one. You can have several dumps if you, for example, if you want to keep separate different aggregates or different nanoparticles, for example, you can write them to separate files, or you can have solvent separate from your target molecules or anything like that. You choose which ones to dump here in the group ID. Here we're just writing all of the atoms to file, and then here it's the what kind of information you're writing to file. Here in custom, we have to tell it exactly what kinds of things we want later. There are, by default, you could have something that just does ID type and positions. Here we're also writing velocities to file. Then you have the frequency of how often you want to write the trajectory file. In this case, every 100 time steps. And then you have the name that you want to the LAMMPS to use to. LAMMPS can append to files that already exist. So if you're continuing a run or anything like that, that is a valid possibility. And then the last thing here is, because we used custom, we then need to tell LAMMPS what information to dump. So we are writing atom ID, atom type, and then the positions and the velocities in all three directions. So let's have a look at the dump file. That's the npt_density.lamps trajectory. Every time step in the dump file will start in the same way with this line item column. And then every item that has item column and then something that will have some lines below, one or more lines below that refer to that section, basically. So it separates the time step in sections. The first thing is the number of the time steps, so time step 0. Then tells you how many atoms are printed, which is 1,000. Then LAMMPS nicely prints us the boundaries of our box and what kind of periodicity they have, if any. It does so in scientific notation, but that can be easily changed. So we have about 10.7 distant Lennard-Jones units in every direction in the 3 dimensions. And then finally, the last section of each time step is the actual dump of atoms, positions, and velocities in this case. But on the item line, LAMMPS will also tell you what each column is. So you'll have a nice legend of what each of the column is. So you'll have, first you'll have the atom number. So that first column here will be the atom ID, atom number. Then you have the type, which in the case of this simulation is just one. We only had one type of atoms. And then I have X, Y, Z positions, the first 3, and then velocities for the last 3 columns. And this will be repeated. So if we go down, after 1,000 atoms, we have the second time step, which is time step number 100. So you can keep track of the number of the time steps here in between every frame of the trajectory, basically. Does that make sense? Any questions about the dump files, the LAMMPS trajectory files? Okie dokie. Let's have a look at slightly different way of writing data to file, but with a different purpose. So, especially because in HPC you might be limited to, X amount of hours of runtime, you might want to periodically save the status of your simulation in a little bit more useful method than just the dump file. The dump file is useful for certain situations, but if all you want is to continue the simulation from where you stopped it, you might want to look into the restart files. Restart files are binary, and that means that you can't read them like we just did our dump file, or just open in a text file and see the data. LAMMPS uses its own way of saving things, but that means that it's also faster to write and faster to read. And it also contains a little bit more information than just atom positions, velocities, and IDs. It contains some of the information for the setup, although not everything. You should be careful about what needs to be set up again when you want to run a simulation from a restart file. But it does have a lot of things. You can write a restart file with same kind of idea as you would for data files or anything like that. So it's just write_restart, and then you give it a name. There are some optional flags here that you might want to have a look on the LAMMPS manual, but for now, this one is the more important. You can do some restarts per CPU thread, for example, that does generate other issues. So unless you really know that you need that, I would stick to this one. One caveat is you cannot usually take a restart file from one system and read it in a different system. Restart files tend to be very system dependent. So the way they are encoded really depend on what the system that LAMMPS was compiled on. And usually you can also not change the number of nodes you're running on. So if you start if you generate a restart file using 4 nodes, you can probably only continue that simulation using not the same 4 nodes, but the same number of nodes. If you want to change the size of your the number of nodes from one step to the other, you'll probably want to write a data file instead rather than a restart file. It's a little bit slower. You need to do a little bit more setup on the next run, but gives you a little bit more flexibility. I tended to write restart files every once in a while when I was running simulations for my PhD or my postdoc. I would tend to run every 100 or 500,000 time steps, depending on the size of the system. I'd write a checkpoint file, basically, so that if the simulation crashed, I could continue from that. And then at the end of the run that I intended to do, being it a few nanoseconds or whatever, I would write a restart file, but also write a read data file, so that that would be a little bit more portable than the restart file. If you want to write a data file, the only difference here, instead of write restart, would be write underscore data. The syntax is pretty much the same for the restarts and the data files. And then to read we have seen how to read data files on the other input, I believe, but it's just read underscore data. To read restarts, same idea, read underscore restart, and then just the file name. And then make sure that you then set up all of the other things that LAMMPS might need. And again, it depends on what kind of simulation you're doing. Any questions about restart files? We can have a look here. So we have an input file here that reads the restart file that we generated with the other one. And this will be part of the exercise in a bit, but if you want to run it, you can launch it now and then it will be ready. You'll need to comment this line here, which is the first, uses the input from the first input file for the first run. And you'll want to uncomment this one that reads the restart file. So I will run that. There we go. Now, I don't see any questions about the restarts. So I will speak a little bit more about computes and fixes and how you can use them how you can use them to calculate properties during your simulations. In this case here, if you noticed on the in.lj underscore exercise file, there are 2 lines here that are calculating a radial distribution function for the system. If you've never heard of an RDF, they basically compare the density of particles a certain amount of distance away from your central particle and compare that to a uniform distribution. So basically, if there's any kind of creations of shell around a particle, the RDF will be able to tell you that. You can do RDFs between, for example, the same types of atoms, of particles, or you can do RDFs between different types of particles. In the case of the simulation, we just have the one type. So the RDF will be calculated for every atom type, every atom of type 1 against every other atom of type 1, and you'll have a radial distribution function between types 1 and 1. The 2 commands here, the compute and the fix, they have slightly different purposes, and the syntax is different. you'll first need to tell LAMMPS that you want to calculate this, and this is done with the compute RDF command. The first variable here, the first parameter here is just the name of the compute. So we're naming it capital RDF, and then we're telling it for what group of atoms to calculate. And then the third parameter is actually the type of compute that we're trying to do. And I believe that last time I checked, there are like 150 different types of computes that you can do. The list is immense, and it keeps increasing with every new version of LAMMPS. The syntax between them will have some similarities, but depending on exactly what you're trying to do, some of the parameters will be different, or some of the flags will be different. So do have a look in the manual about exactly what kind of things you're trying to calculate. So for the RDF, what we give it is the number of bins that we want to do, that we want the RDF to use. So it will be basically a histogram, and we're asking for 150 different bins, and we're telling it to have a cutoff at 3.5 Lennard-Jones units of distance. So that means that anything above that, LAMMPS will not even save, will not write to the RDF file. So that means that we'll have 150 bins between distances of 0 and 3.5. I did not do the math on that, so I don't know exactly the width of the bin, but LAMMPS will do that automatically. However, just because this is calculated doesn't mean that you get any output from that. So if you just do the compute, LAMMPS will happily calculate this, but will not write it anywhere. You need to tell LAMMPS how you want that data to be written. And that's done with a fix. In this case, we're using the average over time fix. Similar syntax. First thing is a name. So the name of the name we're giving this fix is RDF_output. This can be different. And then we're telling it that we're doing this for all the atoms. I have some labels here because there's tons of these things. So this comment line is just the label for each of the parameters that you'll find on the LAMMPS manual, for example. Group ID, all, so all of the atoms. Average time, the type of fix, and then these three values are a source of much confusion. So let's try and demystify this a little bit. Might be easier to go backwards. So this last one, freq and frequency, is how often you want this data written. So you want whatever is calculated, how many averages and how many samples is written to file, and we'll define the name of that later, every 50,000 time steps. So every 50,000 time steps, LAMMPS will write to a file the RDFs that is calculated on average with these two commands. Now, how many samples we want to do is defined by nRepeat, and that is a very mild typo. nRepeat tells you that I want to do 950 samples. So LAMMPS will take values of, will calculate the values of the RDF 950 times, and then at time 50,000 it will write it to file. And the first parameter, every, tells you how often to take a sample. So how many time steps between samples. So if you walk backward from this, from time step 50,000, at time step 50,000, LAMMPS will do the 950th sample with distance between samples of 50. So it will skip the first 2,500 time steps, and then every 50 time steps it will take a sample, and then at time step 50,000 it has the 950 and it will write the file. I do understand this is confusing. You might need to read the LAMMPS manual on this and experiment a little bit to get a handle on it. But this can be incredibly powerful because you don't need to average, for most properties, you don't need to average them every time step. That would delay your simulation quite a lot. So you want to do some sampling every X amount of time steps and then just write that result at the end of your simulation. This is a very good way to do it once you get a grip of what this means. So it is skipping the first 2,500 time steps because we're only asking for 950 samples. And to do 950 samples at 50 time steps between samples and end at time step number 50,000, it doesn't do the first to 2,500 because it only needs 47,500 to have that. It's basically 950 times 50, and the last sample will always be once you write at the time step that you're writing to file. Does that make sense? I have another example on the course material that might be a little bit easier to see and to explain. So if you see on this paragraph, we have with an n every of 2, an n repeat of 3, and an n freq of 100. At every time step that's a multiple of 100, so that means 100, 200, 300, 400, etc. LAMMPS will write to file the RDF that has been calculated so far. It will take averages. It will take 3 samples, 2 time steps apart. So that means that at time step 100, it will write the average of time steps 96, 98, and 100, and it writes that to file. Once you get to 200, you get the same at 196, 198, and 200. So it takes 3 samples, and it counts back from when you want it to write the file. And it will do this every 100 time steps. Does that make sense? Cool. Average over time can be used to get to average some samples over small increments of time, or if you configure it for that, you can basically average over the entire run as well. So that depends on your aim and depends on how you configure it. In this case, we're basically trying to keep a running average of the simulation. We skip the first 2,500 steps because we consider that the system is not in a dynamic equilibrium at that point. That's basically what we're simulating here, and then we're just averaging over and writing it once at the end of the simulation. But if you're interested in the progression of the RDF, and this works for other kinds of properties, you might want more frequent writes, and that's how you would do it. Okay, so now that we dealt with that, we can have a look at the rest of the parameters on this line. So here we're telling LAMMPS what compute to use to do this averaging. So we hadn't tell it yet. So C underscore here means that it's a compute. So it's the output from a compute command. There are other suffixes that we might need to use, and you can have a look at that in the LAMMPS manual. And then this is the name of the compute, so the same as we used there. And then these wildcard, this asterisk wildcard in conjunction with this mode vector here tells LAMMPS to calculate the average for all of the columns that this compute creates. So this compute generates several columns, and this tells LAMMPS to average all of the columns, and not just, if you're just interested in 1 or 2, for example, you could just do that. That would save you a little bit on computation file. And then finally, the file, and then the name of the file is just telling LAMMPS where to write these two. So we're writing to a file, and and we're using this name, so rdf_lj_density, which will be 0.8 in this case, .out. And if we have a look here, we should see rdf underscore lj underscore lj underscore 0.8 .out. If we have a look at here, LAMMPS writes a little bit of our information for us. It tells us what fix we used, and then tells us the labels for the information that it gives. This first line corresponds just to this one, so it's the time step number and the number of rows for the RDF, for the whatever properties we average. So that means there's number of rows in our case is the number of bins, 150. And then we have the legend basically for each of the other rows under the title row, basically, if you will. And this would be as well, you have the row number, so 1 to 150, the bin number as well. Then we have, I believe, the center of the bin, and then you have the number of particles that would fall in that bin, or the whatever property you're calculating, and then finally it's the accumulated integration of the. In the case of the RDF, in other systems these might be different. So here the labels just tell you it's C_RDF_1. You need to check what each compute outputs in the LAMMPS manual. It will tell you there. If you had, so in this case we just wrote once at the end. If you had that example that it's every 100 time steps, you would have many sections that start with time step number and number of rows for every, for example, for the 100, 200, 300 time steps, like the example in the course material. Does that make sense? Okay, let's do a quick exercise. The input, like on the previous exercise, we have the density here. You should be able to change this. I can give you an ideas of try 0.8, then try, for example, 0.1 and something like 1.2. And then we can have a look at the RDFs that it outputs. And then, oh, I need to load GNU plot. With GNU plot, as long as you have started your SSH session with the -x command, and you have on your local machine an X server running, be that Xming or Xquartz for Mac, or if you're on a Linux machine, you're probably fine. You can then use GNU plot and see the output, or you can plot the RDF directly. If we do something like this, I believe using 2 and 3. Yeah, there we go. We have a radial distribution function. Oh, just trying to. There we go. We have the radial distribution function that we calculated. Let's do that with lines. There we go. So you see, we have a very high density at about 1.08. That's the first shell of particles arranged around your central atom. Then you have a second and a third shell, and then it kind of stabilizes. That means that at this distance, there's a higher concentration of atoms than would be expected for a homogeneous system. And then if there's less than one, there's less atoms than it would be expected. So have a look at this, do the exercise. So run it at 0.8, 0.1 and 1.2, and then check the differences between the three densities and see if you can see any difference and maybe have a guess at what's happening. I'll give you guys until the hour, so another 7 minutes or so. That should be enough for that, and then we can have a look at the results from that. I might not have been explicit. You need to run the, let me bring this. You need to run the regular exercise and then the restart, because I believe the RDF is being calculated on the restart. Or no, maybe I'm misremembering. No, never mind. RDF is calculated on the first one. Never mind me. A retry, that means that you didn't start your SSH with the -x, or that your X server command is not configured properly. You can just download the data to your local machine and use GNU-plot there if you have it, or use any other kind of plotting software that you want. Just GNU-plot was just the easiest for me to run, and it's available on ARCHER2. But you do need a little bit of setup with X Windows for that to work. Let me see if I can find any documentation that we have on that. Yeah, that one should work. Yeah, no, the only info we have is that MoXterm includes X server. If you're using something like WSL, you'll need Xming separately, which is what I'm using. If you're on a Mac, you need something called Xquartz. You might need admin rights for some or all of those. I'm not 100% sure. But otherwise, using the GNU-plot command, if you know some GNU-plot, you can set it to write a PNG, for example. And in that case, you can then just download the PNG and open the PNG. Let me see if I can find. The only thing you should need to do is install Xming and then restart your computer, as far as I remember. These might, so with WSL and Xming, if you're not using Windows Terminal, if you're using the default command prompt, I don't know if that works. It might, I don't know. If you don't know about Windows Terminal, it is made by Microsoft, and you can get it on the Microsoft Store. Let me find the. Let me see if I can find a link for that. So Windows Terminal is a Microsoft application that it tells you to install from the Microsoft Store. Don't know why, but yeah, you can get it from there. And as for Xming, it's available on SourceForge, I believe, and I think you just need to install it and restart your computer. It should then work. Okay, that's not entirely true. Depending on the configuration, you might also need this on your terminal. Otherwise, there might be some weirding. So display export display equals :0. If you want, if you don't want the faff of that, you can use the set term PNG Cairo, and I'm typing that on the chat, and that means that GNU-plot will write to a file rather than to a window, and then you can just download the image and open it. Let me just double check that. Yes, you can select the file name with something like this. Okay, has everyone been able to run the simulations at least, even if they're not been able to see all the outputs yet? So I can have a look at the output. The lines are a bit thin, but hopefully we can see the difference here. I just plotted the three of them on top of each other, and if GNU plot updates, there we go. In purple here, we have 0.1, density 0.1. In green here, this one, we have 0.8. And in blue here, we have this one with the bumps, we have 1.2. Does anyone have a guess at why there's such a big difference between them and what might be happening to our system? Remember that this is a Lennard-Jones system that we changed the density between 0.1, 0.8, and 1.2. No one? Well, in Lennard-Jones, in Lennard-Jones systems at these densities, what we have basically is different phases. We have basically a solid phase in the purple at density, gas phase at density 0.1. So we just have the first shell and then maybe a second shell, but not really at larger distances. At 0.8, we have liquid. So we have basically 3 shells around your central atom. And then at 1.2, we have basically a solid, and we see much more order at long ranges and much more pronounced than we do in any of the fluid phases. Okay, anyone still having trouble with RDFs or the simulation itself running the job? Do say something now before we move on. Very good. So we can also run this kind of. That's fine. The GNU plot was just again, like I said, just an easy way for me to show because it's quick for me to plot something. You don't have to use GNU plot. Actually, while I remember, we are outputting these in like text form by default using this file. But LAMMPS, since I think the version 2022 also allows you to write these files as YAML files. So if you then trying to use any kind of plotting from Python, so matplotlib or anything like that, it might be easier for you to write the YAML file and then just read it directly from there. There will be a lot less parsing. I have some info of that on the course material. So if you use the YAML extension, then the output will be a YAML file that LAMMPS can very easily, that Python can read very easily. It's basically Python data structures. So if you're trying to do then matplotlib or pyplot or anything like that, YAML might be the way to go rather than plain text. Okay, so this is the restart script. So the input for a restart run. So we are continuing from that first one we did. So we ran 50,000 time steps. Then we read the restart and we're running it for another 50,000 time steps. And we can create a new compute here. In this case, this is the mean square displacement. Just to give you another example, pretty much all of this is the same syntax as RDF, the same and every and repeat and frequency, the same idea for compute, although here we're just interested in one of the columns from MSD, and then file and a running average rather than a partition one. All of these parameters you'll want to check for whatever property you're interested, but again, we just to give you a second example and to demonstrate that these can be run from a restart. Doesn't have to be if you're only interested in to run these on part of the simulation, you don't need to be running it all along the entire simulation. So if you have some equilibration phase before, you don't need to be calculating it at that point if you're only interested in it later. And to finish before the break, we can have a look at variables and loops maybe. Yeah, let's do that. Might be easier to show here. We have seen variables before. The density we're using it's a variable. We're setting a variable equal to some value. There are many different styles that you can use here for variable. There is, as usual, I put links to the LAMMPS manual. As you can see, there's quite a lot. LAMMPS knows about math functions and group. This is atom groups. So if you're trying to count how many atoms there's in a group, or the mass or charge or anything like that, LAMMPS has functions for all of those things. So if you're trying to do any kind of complicated workflow in LAMMPS input script, it's possible. The syntax can take some use to, but it's possible. Can also unset a variable using the delete keyword. And then there's a couple of special ones that I thought would be nice to highlight for you, which are the loop and the index. They behave in a similar way, but tend to be used for slightly different purposes. The loop one tells you just integer and tells LAMMPS basically to run this part X amount of times and increment the loop variable one every time. So an example here, we're setting the variable a to be a loop type variable of value 10, and then we start a loop. So this would be your for a equals in Python or in Fortran as well, or anything like that. And then you have in between the label and the jump command, you have the code that you want to run many times. So in this case, creating a dump file, running 10,000 time steps, then stopping the dump, and then incrementing A, basically. And so this will be run 10 times. The file will be numbered sequentially, so file.1, .2, .3, .4, etc. And then once jump self is the file, so this file, and then loop goes back to that one. Index is the same idea, but instead of being integers and incrementing, you can give it a list of values to cycle through. So index is basically an array or a list that you can give values. They can be integers, they can be, in this case, we have different runs, so we're just calling them different things so that we can run the same input several times. For example, if you wanted to do some statistical analysis on that, you'd use a slightly different seed for each of them, but then you can do something like this. You can even create different folders and go inside, then you can read your data, run 10,000 steps, and then do the same again for the different runs. I guess in this example, we expect that these folders were already created, and there's slightly different polymers inside of them, but these could be adapted to many things. If there's no questions about variables and loops, I would leave you with these exercise, and we would break for 15 minutes or so. William, yes, but not with this construction. So with this construction, LAMMPS will run these at a time. If you want to run many things at the same time, you need another construction. Either launch many things from the Slurm script, or if you want to do, oh, I'm going to forget the name now. What's it called? Replicate exchange. You need to launch LAMMPS in a slightly different way. We go through replicate exchange in the advanced LAMMPS course. But if the idea is to launch many parallel jobs, you might just be better to launch them from the Slurm script rather than from inside the LAMMPS input script. Okay, so have a look at these LAMMPS rerun exercise at the end of lesson 5. Do let me know if there's any issues. I'll be around, but I do need 15 minutes to go fill up my tea cup because it is empty and cold. I hope everyone had a chance to run the exercises and maybe get a quick cup of tea, maybe some coffee. Were you all able to run the exercise to get a rerun using LAMMPS? There should be a poll on the Blackboard. You could click a button somewhere, say yes or no. Okay, it seems like a large proportion was able to. The others don't have an answer. I'll give you another minute to say if there's any issue before I go through the exercise a little bit. Okie dokie, let's have a look. So to do the rerun, you would have to uncomment this last line on the Slurm batch file to do the rerun instead of the regular run. And if you did that, you would have used the rerun input file, which defines a lot of the same properties as the regular run does. But then at the end, instead of a run and then a number of time steps, what LAMMPS does is reads the positions and velocities from the trajectory file that we created beforehand, and doesn't actually do any force or velocity or acceleration calculations from it. It just reads them from there and then does any kind of thermal calculations if you want them, or even computes from those. So if, for example, you didn't think about calculating the RDF while you run the simulation originally, but you still have a trajectory, you will be able to calculate some RDFs from it. Now, there's a couple of caveats. Is that you can only calculate RDFs for the time steps that you save the positions to, and that also means that you need to adjust these values to be exactly to time steps that exist. So the sample, the sample frequency, these 100 is an every. If you were writing a dump file only every 1,000 time steps, you could have an every being every 100 because there's no data. LAMMPS wouldn't be able to guess what the data would be, so you can only use the sampling can only be done on time steps that exist on your trajectory file. Does that make sense? But the rest is pretty much the same kind of options. And if you plot this output, you'll get a RDF that is very, very similar to the original one that you could create from the original run rather than do that. And that is pretty much all I had to tell you about variables and advanced input files. So unless there's any questions, I'll move on a little bit into GPU acceleration, how you can use it, and maybe talk a little bit about the caveats of those. In the meantime, I'll put up a poll about the last bit, whether you want to have a go at to learn more about compilation, maybe a little bit more about creating some input, some data files to start the simulation with, using some techniques that I've used in the past. It's not necessarily the only ones that exist, or whether you're not interested in any of those and you'd rather just finish for the day. So let me type up a quick poll, and then we'll go have a look at GPU acceleration. Okie dokie. So GPU acceleration. There is one of the exercises that has some files, which I've already run, for GPU acceleration. What you need to know about this is that not every compute file, not every fix, and not every pair style is available for GPU acceleration. So you need, the first time you're using it, or whenever you do massive changes to your input files, you should probably have a look whether the things you're trying to do are available. Now, there's also another issue. Let me bring the course notes here because I'm talking about them. There's also another thing, which is there are two slightly different ways of accelerating LAMMPS using GPUs, or there are two packages that LAMMPS can be compiled with that are slightly different, but both offer GPU acceleration. The Cocos package is the one that was used in ARCHER2 because it's the one that's compatible with ARCHER2 hardware. The GPU package, which in Cirrus, if you have access, LAMMPS GPU there is compiled with the GPU package. Now, the commands you need to run to use them are similar, but very slightly different for if you're using Cocos versus GPU. I have examples here for both. The SRun part will be very much the same or similar. We don't quite define the same things here, but we probably should. If we're running on Cirrus, this is a more general example. If you're running on your workstation, for example. The second part here is the one that has the biggest difference. So we're telling to LAMMPS to use the package Cocos. That's what the PK Cocos means. Then we're telling Cocos to use acceleration on GPUs and to use one GPU. And then these -fx is to tell LAMMPS to add the suffix Cocos, the KK suffix, to every command that that allows it. So you could do this by hand. So go into your input file and add the KK suffix to all of the pair styles and commands and everything. But by passing this flag to your command, LAMMPS just does that for you. If you wanted to use more than one GPU, you change this. Multi-nodes is not been tested on ARCHER2, but it should work on some on Cirrus, for example. It's not usually very performant. You're probably better to stay within one node using GPU acceleration. But as always, benchmark. That's always the best thing. GPUs are able to handle a lot more atoms than a single CPU and even a single node can usually. So you can go quite higher on the number of atoms per GPU that you could on a single CPU node. The example on the exercise actually is, I think, 125,000 atoms, something like that. So it might take a couple minutes to run on ARCHER2, but you should be able to launch it. So you should just be able to launch it with spatch subslur. I did so during the break, and we can have a look at the log file to see a little bit of the differences. The input file, and we can have a quick look at that first. The input file is pretty much the same, so there's no changes here. What we changed was in the submission script. We're telling them to use the Cocos package and adding all those things. The last bit is pretty much the same we had before. The fact that we're doing these Slurm options in the srun command rather than having in the spatch, this is a particularity of the Slurm on ARCHER2 and not necessarily the case in other systems. So you might be able to have these regular normal as spatch commands appear, In the case of Archer2, we need to do this in the srun. Otherwise, Slurm will reject your job and will not run it. So just be aware of that. That's not to do with LAMMPS, that's to do with Archer2. Some of the same applies to servers with slight differences. We do have examples on the documentation of how to launch these jobs. So let's just have a look at the output file. I mean, out of the box, immediately you see that LAMMPS is telling you that is using Cocos and that it's using 1 GPU per node. It's also telling you that's using one OpenM3 OpenMP thread per MPI task like before. If we keep going, at some point, we should have some information. There we go. So we have some similar information about benchmarks like we did with OpenMPI, although there is some extra information on a neighbor list. This is because the neighbor list is now being calculated on the GPU rather than the CPU. And you can see that we are indeed, this took about 2 minutes, but instead of 1,000 atoms, we're running 125,000. So the GPU can handle a lot more, a lot larger file systems, sorry, simulation systems than CPU could. You also see that we're mostly got rid of communication. So most of our time is now spent doing neighbor calculations and modify calculations. We could probably improve, but that's besides the point for this particular exercise. To show you the difference from the Cocos package, the GPU package on, if you use Cirrus, it's very similar. So instead of package Cocos G -K on G1, we have package GPU1 and then suffix GPU. Same idea here with SF Cocos. Question: how can the CPU percentage be above 100%? Let me have a look at that again. 127.1 CPU with 1 MPI task. How did we set up our subslurm? 1 task, 1 CPU per task. That is a very good question, and that really depends on how LAMMPS is calculating that. It's 1 thread, it's 1 task. It is possible that some of the GPU time is being calculated onto it. I'm not 100% sure. Because yeah, it should be running only on 1 task. I'm not sure how, it's going to depend on how LAMMPS is calculating that. That did remind me of something. Here, we're launching LAMMPS with just 1 task and 1 thread. Theoretically, you should be able to get up to 8 CPUs when you ask for 1 GPU in Archer2. Depending on the composition of your system, it might be better or worse to run with more threads or less. Again, benchmark. But yeah, you could theoretically launch this with n tasks equals 8. And in that case, you'd get 8 CPU threads doing some of the work, especially IO stuff, and then the GPU handling the simulation. In certain situations, it can help. In certain situations, it doesn't at all. It really depends on your simulation system. So run a quick benchmark first to see what the optimal number of threads per GPU for your particular system is. And let's see if, okay, 28 megabytes, that might take a while, but we should be able. So the last thing here, just to show you a little bit about VMD, if the file system lets me. So VMD, you might be familiar with it, you might not. Visual Molecular Dynamics. It has a lot of plugins and even functions by default to read LAMMPS data files, LAMMPS trajectory files. It allows you to calculate things. It's a very useful tool for visualization of your trajectory once you run the simulation. We have it available on ARCHER2. It's not very useful for visualizing things on the fly because you're doing it over an SSH connection, but it is very useful, for example, if you want to do any kind of post-processing on your trajectories. You can run VMD on text-only mode without the windows, and you can run all the calculations on ARCHER2 node with more memory than your workstation probably has. Yes, Veto is another option. If you check the course material, it is here. I've personally not used it before much. In my area, we tended to use VMD, and in our group, we tended to use VMD. But I have seen people do amazing things with it. PACMO, we have some instructions on that on the last lesson. And then there's MD analysis, MD trash, PyLat. All of these things can be used to help set up your simulations, post-processing, visualization, any kind of thing. We do not have a Veto on ARCHER2. We do have VMD, and that's why I'm showing this one. Let's see if I can load something. Let's do 0.8. Okay, we can, while that updates, I'm sorry, I cannot increase the font of these windows, but we can already see that it's got 1,000 atoms, 501 frames, so it has properly loaded our trajectory. Again, you'd only be able to open VMD if you have your X server set up properly. The same for GNU-plot. They all work over SSH, over X server. If that's not properly set up, you won't be able to use any of these in the graphical form. You can still run the text, the text command line only. That's of limited use, but it can be useful as well. But if you want all of this, you'll need the X server. You can install VMD locally for smaller trajectories. It works fine on all three major types of operating systems, so Linux, Mac, and Windows. They have native binaries for all of those, so they're very easy to install. The Windows one has a very slight limitation on memory access. It was still compiled in 32 bits, so any trajectory above about 2 gigabytes, you won't be able to open it. But just be aware, for smaller trajectories like this one, 28 megabytes, you'll be able to open it fine. Let me just make this a little bit less line and a little bit more particle. There we go. And let's see if I can make this. So you can see, I don't know how these translates over the Blackboard connection. But you can have a quick look, especially if it's a small trajectory, even over ARCHER2, or you can download the trajectory and look at it from your laptop or your workstation or something. There's loads you can do with VMD. I'm not going to even try to cover most of it, but again, from visualization to then calculation of different properties and lots of things. creating topologies for inputs, for data files, lots and lots of things. Just wanted to make you aware that we do have VMD available in Archer2. Even though over SSH is not exactly fast, it can be useful sometimes to have a quick check of a topology, like a starting topology, for example, or anything like that. I see that the polling showed that most people were interested in both compilation and topology. We do have another hour almost, so I can see if I can squeeze them both in. Let me grab. So I won't do the demonstrations because that would take quite a while to run some of these things, but there is a lesson just for the topology creation, and I'll go through and explain most of this. And there's some gifs of the topologies that we create along the way anyway, so you should be able to understand. This is specifically using PACMOL and VMD. You don't have to use these, but they are useful if you do a lot of fluids with small molecules, for example, with many small molecules. You're able to create this with other tools, like some of the ones I mentioned before, like Pilot and Vito and MDTrash. There's I'm sure there are others, Python packages, for example, that I haven't even heard of. You can use LAMMPS read data command to read read dump to read all sorts of input files. Sometimes you might need to use a VMD plugin to do the processing, but that's fairly easy to link to. You can do PDB, you can do DCD, you can do Amber, Charm stuff. Let me see, I'm pretty sure I have a link. So anything on this list, you can have read dump, read directly. There's a tons of different ones. And yeah, Atom SK, I've never heard of it, so I don't know how it works, but open source command line sounds great. I'm sure that I've never done Crystal stuff. I'm sure that Crystal people will have some specific ones. I'm afraid I won't be able to tell you. But this will be a quick example. The things here, we're starting from a few small XYZ files of water and ethanol, and we're creating a mix of both, but we're creating a like a cube of water in the center and then packing ethanol around it. An example of what to do. PACMOL is also a command line program that reads an input file and then follows the commands that you have there to create another XYZ file with all the packing of all the molecules that you tell it to. For example, here, if we want to create a cube of water, as you can see here on the GIF, a cube of water molecules, we read one XYZ file that has the structure of water, just one molecule, and then we tell PACMOL that we want 1,300 of them inside a cube that has origins 15, 15, 30, so that's X, Y, and Z, and then has a length of 50 on the side. So that's the cube here, the X and Y, which are the red and green arrows, I believe, red for X, yeah, and green for Y, are 15, 15, and then it's 30 units, angstroms, I believe, in this case, off the origin. So that's the blue, the Z direction. And then PACMOL packs all of the 1,300 molecules inside. And the way you run PACMOL is very simply, you call it, and then you pipe in either the commands directly if you want to, or you just give it from a file. And I have all of these files on this lessen material at the bottom. So after we have these cube of water, for example, we can put the ethanol around it. PACMOL allows for many different types of both volumes and even above and below of planes. You can have combinations of inside or outside things like cubes, boxes, spheres, and ellipsoids and cylinders. So you can create fairly complex structures with these. So even things like micelles and almost, I'm sure you could try and create like the simulation of a membrane, but it might be complicated. But you can combine all of these in a row. So in this case, we're telling PACMOL that we want the ethanol inside the larger box, but outside that cube where we just have the water, so that PACMOL doesn't even try to shove any ethanol molecules there. So after we run this input file with PACMOL, well, the result we get is this system that has packed both the water and the ethanol molecules. Unfortunately, PACMOL is getting kind of old, has not been updated in a while, so that AtomSK might be a better option right now if it's been maintained. PACMOL is also just a serial code, so it doesn't run in parallel. Might take a while if it's a very large system. So one suggestion that I have is if you can, and if you have different types of molecules, you might want to do one step at a time instead of doing this here where we do both at the same, not this one, this one where we do both at the same time. You might want to do the water first and then have the water as a fixed structure. So all the molecules of water fixed, and then you're just packing the ethanol around it. So this PACMOL just gives you atom positions, doesn't give you any information about bonds or angles or anything like that. So for that, you might want to use VMD. Like I said before, VMD allows you to even run it on just a command line mode, so you can just pass it the source like script, and it just runs all the commands in the background without any kind of GUI. But that does allow you to automate a lot of things, and especially once you're familiar with your system and you know exactly how the radius you need to give it and all of the things that you need to get all of your bonds and angles correct. It can be quite quick, and you can automate a lot of it. VMD uses the TCLTK language, which can be a little bit weird, but the main loop that you need to do is you need to select a type of atoms. In this case, the atoms are named WO on the XYZ file, so that stands for water oxygen. If we see here, so the XYZ for the water molecule has 3 atoms. We have an oxygen at the center, and then we have 2 hydrogens. And we're using W and WH so that then we can later have them as a different atom type than any oxygens or hydrogens that we have on our ethanol. That just makes it simpler if their force field properties are different, for example, and you're setting them manually. If you're using this if using any kind of force field that's already implemented in LAMMPS, you should probably use the atom types defined there, however they are, being it numbers or letters. So yeah, we're selecting all the atoms that have that are of type WO, and then we're adding some information that the XYZs don't have. So we're adding a mass, so setting it the mass of oxygen. We're creating a LAMMPS, we're giving it a LAMMPS type. We're adding it, we're giving charge to it. We're telling VMD that it's an oxygen. This might be important if you're doing any visualization, but in most cases it might not be. But it might be helpful for you later if you're selecting all of the hydrogens, for example, or something like that. And then we're giving it a radius. This is what's used then to search for atoms that will be bonded together. So if the radii of two particles intersect, then VMD will add a bond to them. So you might need to tinker with this a little bit depending on your XYZ files to make sure that you're getting the correct, all the bonds are the correct ones between your atoms. As long as you didn't pack your system too closely, you'll probably be fine. Hydrogens will obviously have smaller radius, so you should adjust for that. And then you just need to do this a few times for every atom type. And once you have that in VMD, you can source, use the keyword source. That means read and execute the commands in water.tcl. And again, I have the files here if you want to have a look. Source water.tcl, and VMD just goes through that file and executes all of the commands in there. You can also do them by hand if you're testing things, if you're creating things for the first time. You can open the TK console in VMD and run the commands from there. Once you have all the properties of all the atom types set, you can then tell VMD to create a LAMMPS data file from it, and VMD will. If you're running from the TK console, this is not required, but if you're writing a script like I did here, you need to load topo tools because VMD will not do it by default. Here I'm giving you an example of how to create a function if that's something you want to do, depending on what things you're interested in getting. You might want to always calculate some property for your data file to make sure that you have the right things, being it like the number of a certain type of atoms or anything like that. And then in this case, it just gets the total charge of the system to make sure that it is what you expect. In most of my cases, I was trying to run neutral systems. You might be running something with a small charge, but in my case, it would be neutral, or because of slight floating point errors in VMD, you might get something like, something very small, e to the -5, and that is basically 0. It's just the floating point system in VMD is not very good. Last thing, you tell VMD then to recalculate all the bonds between all the atoms. And again, depending on that radii for all of the atom types, it will bond them together, and then tell them to get that data, retype bonds, and then guess the angles between all the bonded atoms, and then guess the dihedrals from all of the bonded atoms, and finally write that as a LAMMPS data file to your file system. The script I have here then prints a little bit more information, like the number of bonds, number of types of bonds, the same for angles and dihedrals, and the total charge. This gives you a quick highlight of the system. If you know exactly how many bond types and bond angles you should have, this gives you information on whether or not your system is good. I use this a lot just in text mode for systems I was familiar with. The first time I usually did this by hand using VMD with the visualizer to make sure that all the bonds were correct. The last thing, VMD will not write any of the force field parameters. So those you'll have to add by hand to the data file, or get them from somewhere else. You could have them on a separate file and read them, the data file that has the positions, and then the data file that has the force field parameters separately, or however you want to do that. There are many ways of creating data files. This is just one that was useful for my cases when I was doing a lot of stuff with polymers that I would create myself. Like I said, read dump can read directly PDBs and DCDs. So if that's the kind of thing you do, you're probably better just going that way. Does that make sense? Does anything you'd like me to expand more on the topology side of things? Okie dokie. So for the compilation, I don't actually have notes written down. I can write them down and add them to the course materials if you guys want. What I can do is show you where we keep our instructions that we use for ARCHER2 and for Cirrus. They are public. And I can go through one of the recent examples and show you what we're trying to do. Give me a second, just get this. Yeah, okay, that works. So I'll paste. So all of the software that's centrally supported by EPCC at ARCHER2 and Cirrus, we upload how we compile our software to these GitHub repo, hpc-uk/build-instructions. The link there points directly to the LAMMPS folder. And for every version that we have currently or that we had in the past, we keep an instructions file on how it was compiled. For LAMMPS, so, oh, I should be showing this. So that looks like this. You can see there's more applications here on the left. There's tons of them. There's also some libraries, some Python environments, and there's also some utilities somewhere. There we go, some utilities. So there's tons of things that we do. Not all of the software is available for all of the systems, but on each of the software folders, you'll see that they usually start with the name of the system that the compilation is for. Then usually the version of the software, in this case LAMMPS, has release dates, and then any further information. In the case of LAMMPS, we usually had what programming environment it was compiled for. In ARCHER2, actually, let me zoom in a little bit because it was a bit small. On Cirrus, we tend to add which MPI library we used also. This is the latest version we have installed on ARCHER2 currently, I believe. It was compiled using the Cray programming environment 22.12. That means Cray Clang 15.0.2. And then we go through all of the commands or instructions that we use ourselves. So if you want to adapt this because you need some more packages from LAMMPS or anything like that, you should be able to follow this, do your small modifications. And then instead of using the paths for the central installations like we have here, you change that to your user path, your files, your folders on your work system, and you can install it locally. So for example, here, first step is to download LAMMPS. We're just making sure that we're downloading exactly the version that we want. If you omit these flags, you'll get the most recent version of LAMMPS, which might be what you want. And then here we're giving it a name to the folder. The next step is to load all of the modules that are needed for LAMMPS. That would be Cray programming environment. They should be loaded by default, but this just makes sure that it is, in case the defaults change anywhere in the future. Cray FFTW, so fastest Fourier transforms in the West, version 3.3.10.3. CMake, Eigen, and in this case, we installed the Python wrappers. So we're also loading Python, adding some path from the Cray libraries to our LD library path, and we're sourcing a virtual environment that was created previously. if you don't want the wrappers, you don't need to do those 2 bits. Then we're going into the folder where we downloaded LAMMPS, creating a new folder for the build process to happen in, and then we are going into that folder. And then this is where the actual setup and compilation happens. You can check a lot of the different flags here on the LAMMPS manual. The important bits here are we are loading one of the presets that LAMMPS comes with, which is the most. These pretty much installs all the packages that don't need any extra libraries or any extra things. We are then adding the MPI package or the MPI option to tell LAMMPS to compile MPI enabled binary so that we can then run in parallel. Using shared libraries, just a way to do that LAMMPS then can use shared libraries rather than static ones. And then we're telling LAMMPS which, or the CMake builder, what's the name of the C++ compiler, what kind of flags, optimization flags we want. That's just -02. These CMake prefix, install prefix, this is where the destination of your installed files will be. So we want to have this path be in your user space. So in this case, it would be /work/ta181/ta181/ your username /something. And then it will install your files on that path, and then you can use them from there. And then we're just giving some information about eigen3, about FFTW, where FFTW is, and this is because we're loading the module. These are defined from there, and the same for this one. And then finally, we're telling where the CMake original files are. And then CMake configures all the build, and then make is actually used to compile. So I explained a little bit of what this is. Let's have a go at this. It shouldn't be too hard, and hopefully we don't encounter any issues. Let's have a go. So first thing, and feel free to follow along and do ask questions if there's anything that I do that doesn't make sense. So first thing I'm doing is cloning. Yes. Cloning the files. So this is the source files that are then going to be compiled. I'm not going to do the Python wrappers this time, so we're just going to do the first 4 modules. So if you don't do the create Python, that one is not needed, I don't believe. You should be able to check that. This one. Yeah, no, that's fine. We have seen the file system have some issues today. CP2212 is not happy. Okay. Let's see if it was anything I had before. Okay. It's probably something that I had before that I wasn't happy with. If you do module restore in ARCHER2, you'll get back to the defaults. Please don't use module purge in ARCHER2 because you won't have all the things you need. Okay. And CMake and eigen. Okay, so now the modules we should have for this are all this. Basically loaded these last 4 here. Adding the Cray LD library paths to our own LD library paths, otherwise LAMMPS won't be happy if you try to run it without it. Now, this is the folder we cloned from GitHub. It's the source files for LAMMPS. Create a build folder, and I'm going to change a directory into it. It should be empty. It is. And now this is where you might want to make a lot of changes. So like I said, here I'm just using a preset that LAMMPS comes with. But if for example, you wanted to add any other packages, this is where you would do it. Let me see if I can find anything that could be useful. Yeah, for example, if you wanted to add the Cocos files here, this is where you'd have to have some more extra configuration. We do have an example of that on the repo. Or netcdf, or any of the ML packages, you'd have to add some extra flags here, depending on exactly what the package is. It would take different flags. The manual on LAMMPS will tell you. So these are the packages with extra build options. So if you were, for example, interested in the GPU command, there's a few more extra flags that you can and should use to set up the GPU package correctly. So this is these flags are going to depend exactly on what you want to build and where. Yeah, make install will work properly. Well, it won't in this case because I forgot to change the path. So actually, let me cancel this. If I go back here, and this is a little bit of a mess because of the way it was copied, the cmake_install_ prefix that we have here, if you change this to be in your user path, in your user folders, 181, ga181 ra/lamps_install, if I do this, then you can make install, and because you're installing to your local user folders without any elevated privileges, you can just make install. You only need sudo privileges if you're trying to install to /user/bin or anything like that. So yeah, I was saying about GPU. If you want any of the extra packages that need some more extra setup, you'll need to read a little bit about what options you need and how to do them. What we do is most of the basic options with the most presets. So for GPU, you'd want the ROCm. I believe it's this one. Yeah, so if you see the instructions that Eleanor did a few months ago, so if it's the file that says ROCm 5.2/3 on the GitHub, it'll give you you can have a look at the differences. So you'll need a few more packages to set up the environment for the GPU nodes, which is slightly different from the regular compute nodes. And you'll also have a lot more options, especially for stuff like Cocos. And here, Eleanor decided to be explicit about the packages instead of just using one of the presets. But the effect is pretty much the same if they're all there, which it looks like it is. All of these instructions, again, are on the LAMMPS manual. The build LAMMPS section is quite detailed. If you can, you should follow the instructions for cmake, which is what we're using here. It tells you about the most basic things if you're doing it on your laptop, for example. It also tells about the presets at some point. I forget exactly where. But yeah, and then there's some basic options, optional settings, extra packages with extra build options. So that's stuff like the GPU or the HDF5 or anything like that. FFTWs that you need to link in, stuff like that. So CMake has successfully generated a configuration. So as you can see here, so it tells us that build files have been written to the folder we're in right now. And if we look here, we should be able to have a look of all the enabled packages. So this will tell you exactly what packages, what LAMMPS packages will be installed. So this is where you'd have a look to see if there's everything you need. It will tell you where it will try to install. So this is in my user space. So if I do, actually that folder doesn't exist, but the one before it should. And does, so it will allow me to install there. And then it gives you some more details of what LAMMPS version it is. It tells you what's the C++ compiler, any flags, any kind of definitions that you might want, Fortran compiler, C compiler, all of that, and some more information, for example, about FFTW and stuff like that. So now the only thing left after CMake does the configuration. You do make, you could just do make, that would do the compilation in serial. Here we can be a little bit more greedy and ask for 8 threads, so it compiles up to 8 files at the same time. There's a few things that LAMMPS might download if it doesn't have it. That means that you wouldn't be able to do that from a compute node. You'd have to do this on a login node. Remember that compute nodes do not have access to the internet. But otherwise, it should take a few minutes and it should hopefully compile. Going back to compiler for GPU, for example, in Cirrus we use CUDA, the CUDA compilers, so NVCC and NV-Fortran. That will depend massively on what system you have. But yeah, for ARCHER2, the ROCm compiler. So Make has compiled most of our object files and is now creating the shared libraries, and we'll create the binary in a second. And then I should be able to just run make install to copy the needed files. There we go. So LAMMPS has been compiled and got the executable. So should be here. Yeah, there we go. So if we do -h, yeah, get all the info. This is all the information on how it was compiled and what things were used and everything like that, and all the packages as usual. So if I do make install, I should get all the files I need to that directory that I set up on the CMake command. And then technically you can delete this folder with the source files and just keep the installation if you don't need to install it again. And you should be able to also add that installation folder to your path if you want to use that installation instead of the central one. If you're building for your project instead of just for yourself, you could do, instead of your user folder, you could do in the shared folder. And in that case, you can also create a module file the same way we do our central ones. If you're interested in that, do send us an email. We'll be happy to work with you in creating those. They're not complicated, but there might be some tricks involved. If you want to install like I said, if you want to create a module file for your entire project, for example, I'll be able to help you with that. So yeah, installed on this folder. So if I now go here, we should have regular folders from any installation, including libraries, include files, any manual files as well. And there's all the force field here, I believe in share. yeah, first potentials. Yeah, so all of the stuff is here, and then the binary is in the bin folder. So if now instead of using the module, I use this executable, it should be able to run exactly the same way it does with the central module, because it basically is the same compilation process. We didn't do any changes. However, if you had added any packages or any of the ML packages, for example, you'd be able to use those because we do not have those installed in the central module. Any questions about compilation or any other thing? To be fair, that was the last thing I had for today. Yeah, Tobias, the GitHub is linked on our documentation, I believe. We every time we install a new version, we add a new file with the what we used, as much as a reference for ourselves later on as it is for users that might need to use it. Like I said, we have that for all of the software we install centrally, and for a few that we do not support centrally but do sometimes help people install on their own user accounts. William, I'm almost 100% sure it won't be online today, but it will be online this week. Oh, sorry, I misread. You said someday. My bad. Yes, at some point this week, it will be uploaded. Okay. Well, if there's no questions, feel free to go and have a great day and a great week.